All right, welcome back. Dr. P here, and in this lecture we're going to move on into Chapter 21, which of course is intimately tied to Chapter 20 because Chapter 21 deals with carboxylic acid derivatives. And of course we will also revisit nucleophilic acyl substitution. So let's look at some carboxylic acid derivatives. Okay, so I did talk about this last time. We could have an acid halide where X equals chlorine or bromine. So I think I gave you the example of an acid chloride before. We could have an acid anhydride. We could have something called a thioester. We could have a regular ester. We could have an amide. And we could have let me see here, how many, double bond there, negative charge, negative charge. We can have an acyl phosphate. And that in particular is biological. Thioesters are often also biological. And of course, last time we saw that a nitrile is a carboxylic acid derivative. Okay, and again, all of these are derivatives of our carboxylic acid. So let me just scoot this up a little there, carboxylic acid. Now, for this class, we are really going to focus on this stuff over here. In particular, we'll be focusing on, I did mention nitriles, but we're going to take a look at these four carboxylic acid derivatives and their relationship to carboxylic acids as well. Nitriles are kind of their own little thing. Now, all of these carboxylic acid derivatives will undergo nucleophilic acyl substitution. So just a little review, let's look at nucleophilic acyl substitution. Okay, we have some kind of carboxylic acid or carboxylic acid derivative. And so I'm going to put a Y there. And then we'll react that with a nucleophile, we'll call it nuc minus, and we will get RC double bond O nuc plus Y minus. And we did go over the mechanism briefly back in chapter 20, lecture 2, I think. Let me find it here, so I don't have to draw it out again. Hold on here. Here's lecture 2. We didn't, here's lecture 2. The mechanism was one that I did go over in person. So let's go over it again since it's not in the lecture videos. And this is kind of the general, let me call this the general mechanism. We've got R, C, double bond O, lone pair, Y. And then we've got our nuke minus, and we get nucleophilic attack, and we form something called the tetrahedral intermediate, which I may have spoken about earlier. And then we can get loss of leaving group to give us R, C, double bond O, nuke, plus Y minus the lone pair there. All right. Now, not all nucleophilic acyl substitution reactions are equal. So not all carboxylic acid derivatives have equal stability. So some carboxylic acid derivatives are more stable than others. In particular, we're going to look at the stability of the leaving group. So a good leaving group is going to equal a less stable or more reactive carboxylic acid derivative. So for example, if we took a look at an acid chloride, and let's say we reacted this with some nucleophile, we get RC nuke plus Cl minus. Let's compare this to the other end of the spectrum here, where we have an amide, and if we were to do nucleophilic acyl substitution, we get an NH2 minus. So in the scheme of things, we have this guy here is stable, and then this guy over here is unstable. It's a strong base. Okay, NH2 minus is a very strong base. So because the Cl minus is more stable, our acid chloride is more reactive or less stable. Now there's another way of looking at this as well, and it's looking at the actual resonance structures that you could draw of the carboxylic acid derivatives themselves. So one way of looking at the reactivity of carboxylic acid derivatives is to look at the stability of the leaving group when you do nucleophilic acyl substitution. The other way is to look at resonance structures of the carboxylic acid derivatives themselves. So we'll say, or look at resonance structures of carboxylic acid derivatives themselves. And so we would have, let's say with our acid chloride, we'll go ahead and push some electrons around. We have a not very great looking resonance structure there. Not great. Why is it not great? Well, in addition to the negative on the oxygen, which is fine because, you know, we've got OH minus, that exists in solution. The key here is we've got charge separation and a positive charge on chlorine, which is not really that happy. Now you can do this for the other carboxylic acid derivatives as well. I'm just going to do it for amides because, again, these are the extremes of the carboxylic acid derivative reactivity spectrum. And in a slide in a minute, I'll go ahead and summarize that. But let's take a look at our resonance structure here. I get a CN double bond and a positive charge on the nitrogen. So that positive charge on the nitrogen is not that bad. In fact, amides actually have a significant amount, of partial double bond character between the carbon and nitrogen. It's one of the things that makes proteins fold up the way they do. These aren't actually single bonds. They don't function like single bonds. There's a barrier to rotation, and they have partial double bond character. So, not great, less stable, more reactive. Not too bad, more stable, less reactive. So we can kind of summarize these, and we'll look at the major ones here. So let's look at reactivity. I'll draw a couple of diagrams here. Okay, so at the top, we've got most reactive. Is our R, C, double bond O, X, acid halides. Down at the bottom, our least reactive is going to be our amides. Okay, and technically, I mean, I would say probably a carboxylate is actually going to be the least reactive. So let's throw that in here. So we'll call that the really least reactive. And the next, in the next diagram I draw, I'll show you, what I'm talking about here. So less reactive than acid halides are the acid anhydrides. And then less reactive than the acid anhydrides are the thioesters. Again, these are biological, and then less reactive than that are regular esters. I don't remember where the acyl phosphates fit into things. They're relatively, phosphate group is pretty, I think they're probably around, thioesters as well. So anyway, we can look at the leaving groups and see here, X minus, good leaving group. Carboxylic acid, or carboxylate salt, good leaving group. R prime S minus, better leaving group than R prime O minus. So alkoxide, the sulfur version, is more stable. You may remember that from Chem 12A. And then amides at NH2 minus, not a good leaving group. Okay, so how would we change from one of these to another? Well, we can interconvert. Let me move that so you can see the carboxylate ion there. I know, sorry, squeezing things in here. But let me draw the following diagram to show you how they're related and how we interconvert between the different carboxylic acid derivatives. Essentially, we can only go down this reactivity chart. We can't go up, with one exception. So let's look at nucleophilic acyl substitution. In particular, we'll look at interconverting between the carboxylic acid derivatives. All right, so at the top, our most reactive, we've got our acid halides, our acid chlorides. And next, we've got our acid anhydrides. And next, we have our, let's do some different colors here. Let's do it in blue. Yeah, why not? We've got our R, C, double bond O, O, R prime, our esters, and then our least reactive derivative is our amide. And so we can convert these, but we can only go downwards. So from most reactive to least reactive. And let me just say most reactive and least reactive. So let's say I wanted to convert my acid chloride to an acid anhydride. I'd want to use as my nucleophile RC double bond O, O minus. That would be my nucleophile. Now, if I wanted to convert an acid chloride to an ester, or convert an acid anhydride to an ester, I could do either one. I'll use R prime OH. And then to get my amide, I can do any of those three, the ester, the acid anhydride, or the acid chloride, and I would use we would do NH3. We would do ammonia. Okay. Now I could have R groups there instead, so I could have some substitution there, in which case I'd use an amine instead of ammonia. But this would give me, ammonia gives me that particular amide. Now all of them will actually undergo all of these guys will undergo hydrolysis. And with the more reactive species, so like the acid chloride and acid anhydride, you can just throw water in and it will hydrolyze these guys to the carboxylic acid or the carboxylate ion. For esters and amides, you need to have some acid or base catalyst. And for amides, you need to have more concentrated acid or base and heat it up. Now, so let's say you actually, you had a carboxylic acid and you wanted to make an amide, let's say. You can't really go straight that way. There's a way to do it outside of this sort of scheme, and we'll talk about that later. But what you do is there is a reaction that will take you from this guy here all the way back up here. And that's using thionyl chloride. Sorry, that's a 2. Come on, Wayne. SOCl2. Okay, thionyl chloride. Let me scribble that out and write it in again. SOCl2. Okay. So that's called thionyl chloride, and it's a way to convert the thionyl chloride is a way to convert a carboxylic acid into an acid chloride. So let's say you wanted to turn an amide into an ester. You can't do that directly because even if you're ROH or RO minus, that's not a bad nucleophile. The NH2 minus is a worse leaving group. So we can't go backwards like that. But what you could do is hydrolyze the amide to a carboxylic acid, treat it with thionyl chloride to go back to the acid chloride, and now react it with an alcohol and get your ester that way. So I kind of like this table. It's a nice summary, if you will, of how things are interrelated. All right. So let's see, I did go over that core mechanism for nucleophilic acyl substitution, the general mechanism. And we'll talk about some specific examples in the next lecture video. I'll go through some specific examples, and then in the video after that, I think I'll talk about some individual types of reactions that the different carboxylic acid derivatives can undergo. Okay? All right. So until then, stay safe out there, and I will see you later. Bye now.